Hello, my name is Alexander Miramontes, and today I'll be presenting my Physics 2212 Lab 5 report. To start, in this lab, I had to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare the computational predictions with the observed data. The concepts used in this lab are the magnetic field of a bar magnet, which is simply a dipole, magnetic flux with its time derivative, Lenz's law, Faraday's law, the momentum principle, Ohm's law, and the magnetic force of a falling magnet caused by a current carrying loop. For this experiment, I used a tube of aluminum foil and then dropped a bar magnet into it. The found values are as shown. The magnetic moment was found in Lab 3. After conducting 5 trials of this experiment, the average time to fall through the tube was 1.26 seconds. This is close to the computational model's time of 1.32 seconds. Some questions during the lab were, why can't we use a ferrous tube, for example, a steel pipe? Well, it has iron and could become an induced magnet, causing interference with the falling magnet. And also, what happens to the magnet? How does this compare to a magnet falling in free space without a tube? Well, the magnet will fall slowly in the tube, and it's slower than if it was dropped without the tube. For the code of my computational model, in step 1, the tube's geometry was used. In step 2, I defined the magnetic field of a dipole at any location using the formula for it. In step 3, the time derivative of flux was calculated, and in step 4, the current of a single ring of the tube was found using the code shown. In steps 5 and 6, the force was calculated by the induced current of the falling magnet. In step 7, the force due to gravity was calculated, and the net force, which accounts for the force due to gravity and the force due to the induced current. In step 8, the momentum principle was used to update the velocity and position of the magnet as it falls through the tube. The final results are shown as follows. In the graph, it's seen that velocity increases, then decreases, and then settles at around 0.23 meters per second for around 1 second. Then the magnet reaches the end of the tube and falls out completely. The time in tube was 1.32 seconds here in the computational model, and earlier the actual time in tube was 1.26 seconds, as this value was taken after 5 trials. And now for the discussion questions. The intensity of the coloring of the tube indicates the magnitude of current flowing through each ring. Which color corresponds to clockwise current and which counterclockwise? When you apply Lenz's law, it's clear that red is counterclockwise and blue is clockwise. It's because of this that slowed the magnet down. What happens to the dynamics of the system when you flip the magnet around? Nothing would happen. It will still be slowed down, but now the currents will flow in opposite directions from the initial position. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? The model used was accurate, just a tiny difference in results. To make the model better, we could make the tube into more rings to get a more accurate time, and also consider error and resistance the magnet might face as it goes down through the tube. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? When referring back to the graph, the forces are unbalanced in the first section of the graph. The speed is increasing. The forces are still unbalanced in the other direction when the speed is decreasing. Then the forces will balance for a second during the flat section. Then the forces are unbalanced again as speed increases. For the first what-if question, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The braking force increases to a point where it balances the gravitational force and prevents the magnet from falling through the tube altogether. For the second what-if question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would disrupt the normal flow of current through the rings of current in the tube. What's going to happen is that the braking force would not be as strong due to a reduced amount of current being able to flow through the tube.